Every map you've ever seen is missing a continent. Not a myth, not a legend, an actual landmass nearly 2/3 the size of Australia, with mountains, forests, and coastlines that stretched for thousands of kilometers. Zealandia existed for hundreds of millions of years before it disappeared beneath the Pacific Ocean, and the strange part is this. There's no crater marking where it went, no ash layer recording its destruction, no sudden extinction event in the fossil record. It simply sank, slowly and silently, until only the peaks remained above water. Scientists confirmed it as Earth's 8th continent only in 2017, and the story of how it vanished and how we found it again rewrites what we thought was possible for an entire continent to do. Zealandia sits beneath the waves east of Australia, covering roughly 4.9 million square kilometers of the Pacific seafloor. That makes it larger than the Indian subcontinent, larger than Greenland. If you drained the ocean, it would rival Europe in size, minus Russia, but 94% of it is submerged, hidden under between 1 and 2 kilometers of seawater. Only 6% breaks the surface. The islands of New Zealand, New Caledonia, and a handful of smaller outcrops scattered across the South Pacific. On a standard world map, these islands look isolated, like random volcanic peaks dotting empty ocean. They're not. They're the mountain ranges of a drowned continent, the highest elevations of a plateau that once stood above sea level. The seafloor surrounding them doesn't plunge immediately into the abyss. Instead, it forms a broad, elevated platform sitting roughly 1,000 to 1,500 meters below the waves. Beyond that platform, the true ocean floor drops away to depths of 3,000 to 4,000 meters. Zealandia rises above its surroundings like a submerged table, distinct and massive, separated from Australia by a deep trench called the Cato Trough. The continent meets every geological criterion that defines a continent. It's elevated significantly above the surrounding ocean floor. Its crust is thick, 10 to 30 kilometers in places, compared to the thin 7-kilometer crust of typical ocean floor. It's made of continental rock, granite, metamorphic schist, sedimentary basins, and it has well-defined boundaries, a unified structure that extends from the subtropics down toward the Antarctic. Geologists don't dispute these facts. The only reason Zealandia doesn't appear on classroom globes is that it's underwater. Continents aren't defined by whether you can walk on them. They're defined by what they're made of and how they behave. Ocean floors are built from basalt, dense, heavy rock that forms when magma wells up at mid-ocean ridges, cools quickly, and spreads outward. Basalt is dark, fine-grained, and chemically simple. It's the planet's factory flooring, churned out steadily and recycled back into the mantle at subduction zones. Continental crust is different. It's made of granite and similar rocks, lighter, thicker, chemically complex, and much older. Granite forms deep underground from slow-cooling magma, and it doesn't recycle easily. It floats. That buoyancy matters. Earth's outer shell, the lithosphere, floats on the semi-fluid mantle below. Thick, low-density continental crust rides high. Thin, dense oceanic crust sinks low. Zealandia is made of the same granitic, metamorphic, and sedimentary rocks you'd find in the cores of Australia, South America, or North America. Rock samples from New Zealand's South Island, from New Caledonia, and from the smaller islands scattered across the region all come back as continental material. Some of those rocks are over 500 million years old, dating back to the Cambrian period when complex life was just beginning to diversify. The crust is also thick enough. Oceanic crust averages about 7 kilometers. Zealandia's crust ranges from 10 to 30 kilometers thick. That's thinner than most continents. Australia's crust runs 30 to 45 kilometers thick, but it's still distinctly continental in structure. The thickness isn't uniform. Some areas are more stretched than others, but the overall pattern is clear. This is not ocean floor dressed up as a plateau. It's a continent that lost its buoyancy. Zealandia is also a single, continuous landmass, not a scattering of fragments. The Cato Trough separates it cleanly from Australia. To the south, it extends toward the Antarctic continental shelf, though the exact boundary is harder to define because of ice and deep water. To the north and east, it tapers off into the truly deep Pacific Basin. Satellite gravity mapping which measures how the ocean surface bulges slightly over massive underwater features, shows Zealandia as a unified structure, a coherent geological entity wrapped around New Zealand like a drowned scaffold. It's not almost a continent. It's a continent that happens to be 1,500 meters too low. 100 million years ago, Zealandia wasn't separate. It formed the eastern flank of Gondwana, the southern supercontinent that included South America, Africa, India, Australia, and Antarctica. Zealandia was fused to the eastern edge of Australia and the northern edge of Antarctica, part of a continuous landmass that stretched from the tropics to the South Pole. Plants and animals moved freely across these connected regions. Southern beech trees, Nothofagus, spread across all three landmasses. So did the ancestors of the animals that would later become uniquely New Zealandish, the ratites that would evolve into moa and kiwi, the reptiles that would become tuatara. Around 85 million years ago, the tectonic plates began to shift. A rift opened between Zealandia and Australia. Rifting doesn't happen suddenly. It's a slow mechanical process driven by convection currents in the mantle below. As the mantle flows, it drags the overlying crust in different directions. When two pieces of continental crust are pulled apart, they don't snap like a brittle stick. They stretch. The best analogy is pizza dough. Start with a thick ball of dough. That's the original Gondwana crust, 40 kilometers thick. Pull the edges apart. The dough stretches. The edges stay thick because they're not being pulled, but the middle, the part being stretched, gets thinner and thinner. The same thing happened to Zealandia. As Australia moved northwest and Antarctica moved south, Zealandia stayed in between, getting pulled in both directions. The crust stretched. In some places, it thinned from 40 kilometers down to 20 kilometers or less. The surface area increased, but the volume didn't. The continent got wider and thinner at the same time. By about 60 million years ago, the separation was complete. Zealandia was no longer attached to anything. It drifted as an independent microplate, caught between the Australian plate to the west and the Pacific plate to the east. But the stretching had consequences. When you thin out continental crust, it loses buoyancy and settles lower into the mantle. Zealandia, stretched to half its original thickness, could no longer ride high enough to stay above sea level. The land didn't collapse into a hole. It simply adjusted to a new equilibrium, sinking slowly as the mantle beneath it cooled and contracted. The principle is called isostasy. The lithosphere, Earth's rigid outer shell, floats on the hot ductile mantle below. A thick slab of low-density granite floats high on the denser mantle, just as a thick piece of wood floats higher in water than a thin sliver. Zealandia's crust, stretched thin, lost the volume it needed to stay above the waves. But the stretching itself wasn't the only mechanism. Rifting generates heat. As the crust pulls apart, hot mantle material wells up beneath it, heating the lithosphere from below. Hot rock is less dense than cold rock, so the heated crust actually floats a bit higher during the active rifting phase. This is why rift zones often have high elevations. Think of the East African Rift, where the land is elevated even as it's being pulled apart. Zealandia likely experienced the same effect. During the stretching phase, parts of the continent may have remained above sea level, kept afloat by the heat from below. Then the rifting stopped. Around 60 to 50 million years ago, the tectonic forces that had been pulling Zealandia apart ceased. The continent settled into its new position, no longer being actively stretched. Without the stretching, the heat source disappeared. The mantle beneath the crust began to cool. Cold rock is denser than hot rock. As the lithosphere cooled, it contracted. As it contracted, it got denser. As it got denser, it sank lower. This process, called thermal subsidence, took millions of years, but the result was inevitable. Zealandia, already thinned by stretching, sank even further as it cooled. By around 50 million years ago, the vast majority of the continent was underwater. The sinking was gradual. There was no sudden catastrophe, no tipping point where the land gave way. It was a thermodynamic adjustment, a slow settling into a new gravitational balance. difference. The sea level didn't rise to cover Zealandia. The land sank beneath the sea. The ocean simply filled in the space the continent vacated. The highest peaks, the mountains that are now New Zealand's North and South Islands, stayed above water. The rest disappeared, not erased, just relocated 1,500 meters lower. Before it sank, Zealandia was a living landscape. We know this because of what geologists found buried in the mud beneath the Pacific. In 2017, the drilling ship Yoetes Resolution sailed to 6 sites across the northern and eastern edges of Zealandia. The ship carried equipment capable of drilling hundreds of meters down through the seafloor, pulling up long cylinders of sediment that record the history of the region, layer by layer. The International Ocean Discovery Program funded the mission, Expedition 371, with the explicit goal of understanding what had happened to Zealandia. The drill bit passed through the top layers of sediment, fine gray-brown ooze made of the shells of microscopic organisms that live in deep water. These layers are recent, geologically speaking, deposited over the last few million years. But deeper down, the sediment changed, at depths corresponding to the Eocene epoch, roughly 50 to 35 million years ago. The cores brought up something different. The sediment was coarser. It contained shells of foraminifera, tiny single-celled organisms that live in warm, shallow, sunlit water, and mixed in with those shells were fossilized pollen grains. Pollen doesn't survive in the deep ocean. It's organic, fragile, and it degrades quickly in oxygenated water. The pollen in these cores came from land plants. Warm climate ferns, southern beech trees, other species adapted to temperate rainforests. The only way that pollen could have ended up in sediment, now sitting 1,000 meters below sea level, is if it had been deposited in shallow water or on dry land, then buried as the seafloor subsided. The cores proved that parts of Zealandia were above water, or at most in very shallow seas, 50 million years ago. They proved the continent had forests. Reconstructing the landscape from pollen and microfossils is indirect, but the picture is consistent. Zealandia in the Eocene was warm. The planet as a whole was much warmer than today. There were no ice caps at the poles, and even high-latitude regions supported lush vegetation. Zealandia, though located far south, wasn't frozen. The land was covered in temperate rainforests, dominated by southern beech and tree ferns, similar to the forests that survive today in isolated pockets of New Zealand's South Island and in Tasmania. The climate was wet, the soil was rich, and the coastlines were complex. Internal seas, archipelagos, mountain ranges that have since been eroded or submerged. The forests weren't empty. Before the asteroid impact 66 million years ago, dinosaurs roamed Zealandia. Fossils of theropods, sauropods, and ankylosaurs have been found in the Chatham Islands and on New Zealand's North Island. These aren't the complete skeletons paleontologists dream of. Zealandia's geology and the subsequent submergence make preservation difficult, but they're enough to confirm that non-avian dinosaurs lived here. Somewhere beneath the Pacific, on the submerged plains and valleys of Zealandia, there are likely more fossils, bones, tracks, nesting sites. They're inaccessible, locked under a kilometer of water and sediment, but they're there. After the dinosaurs died, new creatures evolved to fill the empty niches. Giant penguins appeared on Zealandia's coasts. Crossvalia waiparensis, discovered in Waipara on New Zealand's South Island, stood 1.6 meters tall, roughly human height. It lived around 60 million years ago, shortly after Zealandia began to separate from Gondwana. The isolation of the continent allowed unique evolutionary paths. The ancestors of New Zealand's flightless birds, moa, kiwi, kakapo, were stranded on Zealandia as it drifted away. With no large mammalian predators, these birds lost the ability to fly and evolved into giants. All of this happened on a continent that was, for a time, an isolated biological arc, drifting through the South Pacific. Zealandia stayed hidden for most of human history because you can't see through 1,000 meters of ocean with telescopes or satellites. Early seafarers crossing the Pacific had no idea they were passing over a drowned continent, even Even when oceanographers began mapping the seafloor in the 20th century, they only gathered data in narrow strips following ship tracks. The maps they produced showed underwater hills and ridges around New Zealand, but not the big picture. Without comprehensive data, the hills looked like isolated features, not the edges of a unified plateau. Geologists working on New Zealand and New Caledonia knew something was strange. The rocks they found, granite, schist, old sedimentary formations, were continental, not the basalt you'd expect from volcanic islands. But the assumption was that these were fragments, continental crumbs left behind when Gondwana broke apart. The idea that they were the peaks of an intact, submerged continent seemed too large to consider. There was no framework for it. Continents were land masses you could walk across. If it was underwater, it was the ocean floor. The breakthrough came from space. Satellites equipped with radar altimeters can measure the height of the ocean surface with millimeter precision. The ocean surface isn't flat. It has permanent bumps and dips caused by the gravitational pull of massive underwater features. A submerged mountain range pulls water toward it, creating a slight bulge on the ocean surface directly above. A deep trench lets water sag slightly. By measuring these variations across the entire Pacific, scientists could map the shape of the seafloor without sending a single ship. When geophysicists analyzed the global gravity maps, they saw something remarkable. A large, coherent structure wrapped around New Zealand, elevated above the surrounding ocean floor, with well-defined edges and a unified shape. The gravity map revealed Zealandia's continental form. It wasn't a scattering of isolated ridges. It was a plateau, continuous and massive, stretching from New Caledonia in the north to the subantarctic islands in the south. The data had been there for years. It just required someone to look at the full picture and recognize what it meant. Bruce Luyendyk, a geophysicist at the University of California, coined the name Zealandia in 1995. But the concept didn't gain traction. It was treated as a curiosity, a piece of geological jargon, not a serious claim about the number of continents on Earth. The data remained scattered across different disciplines: geologists studying rock samples, oceanographers mapping bathymetry, geophysicists analyzing gravity anomalies. No one had synthesized it all into a single argument. That changed in 2017. Nick Mortimer and a team of researchers from GNS Science in New Zealand published a paper in GSA Today laying out the case systematically. They compiled rock samples, gravity maps, bathymetric surveys, and crustal thickness measurements. They showed that Zealandia met every geological criterion for a continent. They demonstrated that it was a unified structure, not a collection of fragments. Mortimer summed it up simply: if you could pull the plug on the world's oceans, it would be clear to everybody we have mountains, continents, and plateaus. The paper didn't discover new data. It integrated existing evidence and made an argument the scientific community couldn't ignore. Zealandia was a continent. It had always been a continent. We just hadn't been looking at it correctly. The gravity maps and rock samples made a strong case, but they didn't prove Zealandia had been above water. Continents can be submerged without ever having been dry land, if they formed underwater and stayed there. To prove Zealandia had been a living terrestrial landmass, scientists needed biological evidence. They needed fossils from organisms that can only live on land or in very shallow water. That's where Expedition 371 came in. The JOIDS Resolution is a massive research vessel, 143 meters long, equipped with a derrick tower that rises 61 meters above the deck. The ship can drill in water thousands of meters deep and pull up cores from hundreds of meters below the seafloor. In the summer of 2017, it sailed to 6 drilling sites across the northern and eastern edges of Zealandia. The mission lasted 2 months. The cores the crew recovered span millions of years of sediment, each layer representing the conditions at the time it was deposited. The top layers were predictable: deep ocean sediment, the kind you'd expect from a region that's been underwater for tens of millions of years. But as the drill bit went deeper, the sediment changed. At depths corresponding to the Eocene, roughly 50 to 35 million years ago, the cores brought up sediment that didn't match the deep ocean. The shells of foraminifera in these layers were from species that live in warm, shallow, sunlit water. The sediment itself was coarser, the kind deposited in lagoons or coastal environments. not the fine ooze that settles in the deep sea. And then there was the pollen. Fossilized pollen grains from land plants, ferns adapted to warm climates, southern beech trees, other species characteristic of temperate rainforests. Pollen is delicate. It degrades quickly in oxygenated water. The only way pollen ends up in marine sediment is if it's deposited close to shore, in shallow water, where organic material from the land can accumulate before it breaks down. The presence of pollen in sediment, now sitting 1,000 meters below sea level, meant that sediment had been deposited when the seafloor was much higher, when it was dry land or very shallow water. The cores also contained spores from ferns and microscopic plant material that confirmed the pollen findings. Together, these fossils painted a clear picture. Between 50 and 35 million years ago, large parts of Zealandia were above water, covered in forests, and surrounded by shallow seas. The land didn't sink all at once. It subsided gradually, piece by piece, over millions of years. The forests disappeared as the ground beneath them settled lower and the ocean crept inland. By 35 million years ago, most of the continent was gone, leaving only the highest peaks above the waves. The core samples were the smoking gun. They proved Zealandia wasn't just a submerged plateau that had always been underwater. It was a drowned continent, a landmass that had once supported ecosystems, forests, and possibly animals we'll never fully catalog. The fossils trapped in the mud are the only record left of that world. Zealandia is still moving. The continent may have sunk 50 million years ago, but the tectonic forces that shaped it didn't stop. Around 25 million years ago, the Pacific Plate and the Australian Plate, the two massive slabs of lithosphere on either side of Zealandia, began colliding. The boundary between them runs directly through the middle of the submerged continent, cutting across what is now New Zealand's South Island. This collision is the reason New Zealand exists as dry land. While the rest of Zealandia subsided from stretching and cooling, the narrow strip where the plates meet is being compressed. The Pacific Plate is diving beneath the Australian Plate in the north, and the Australian Plate is diving beneath the Pacific Plate in the south. In the middle, where neither plate wants to give way, the crust is crumpling upward. The Southern Alps, the mountain range that runs the length of New Zealand's South Island, are the result of this ongoing compression. They're rising measurably, pushed up by the same tectonic forces that are pulling the seafloor apart elsewhere. The Alpine Fault marks the plate boundary. It's one of the most active fault lines in the world, capable of producing massive earthquakes. Understanding the structure of Zealandia, the thickness of the crust, the distribution of faults, the stress patterns in the lithosphere, help seismologists predict where and how future quakes will strike. The submerged 94% of the continent isn't geologically inert. It's part of a living, deforming system that directly affects the 6% we can see. In 2009, the New Zealand government and GNS Science began using the dual name Te Rua Maui alongside Zealandia. Te Rua Maui means the hills, valleys, and plains of Maui in Maori. The name references the demigod Maui, who, according to tradition, fished up the North Island from the ocean depths. The South Island was his canoe. The myth and the geology mirror each other. The land did rise from the deep, not all at once, but through tectonic uplift over millions of years. And a massive fish, the submerged continent, does lie beneath the waves. Zealandia's recognition as a continent has practical implications. Under the United Nations Convention on the Law of the Sea, countries can claim exclusive economic rights over their continental shelf, the submerged extension of their landmass. Because New Zealand sits on a continent, not just an island arc, its territorial claims extend across an area roughly 15 times larger than its visible landmass. That territory includes potential oil and gas reserves, mineral deposits, and deep sea resources. Whether New Zealand will exploit those resources remains a contentious question, but the legal framework depends on recognizing Zealandia as a continent. The discovery forces a broader reckoning. There's no governing body that decides what counts as a continent. Geologists, geographers, and educators all use slightly different definitions. Some count 4 continents, others 5. And most say 7. Zealandia makes the count 8, if you accept that a continent doesn't need to be above water to be real. The resistance to that idea isn't scientific, it's perceptual. We define geography by what we can see and walk on. Zealandia asks us to redefine it by what the planet is, regardless of where the ocean surface happens to be. New Zealand isn't an isolated island chain, it's the mountain range of a drowned continent, the 6% that refuse to sink. The rest of Zealandia is still there, still intact, still a continent by every measure that matters. It's just 1,500 meters too low for us to notice without looking carefully. And now that we've seen it, the map of the world has to change.